The next several of these little video lectures are going to address cyclohexane and substituted cyclohexanes because it gives us a really good opportunity to look at constitutional isomers where things are attached differently, geometric isomers where different groups are pointing in opposite ways with respect to each other or in the same way, and then conformational isomers where rotation about single bonds can move things from one position to the other without breaking bonds or changing the identity of the molecule. So constitutional isomers are actually different molecules with the same formula. Geometric isomers are different molecules with the same formula. Conformational isomers are just different temporary shapes of the molecule where it's the same molecule that's moved and changed its appearance. And so with the cyclohexanes and substituted cyclohexanes, we get to see examples of all of these, and it's a really cool molecule in that it's very highly symmetric. It has a variety of conformational isomers. We're going to stick mainly with what's referred to as the chair form of cyclohexane. I think it looks more like a crown than a chair for me, but the way it's traditionally drawn is in the shape of a chair, so that's where the name comes from. So cyclohexane, again, we're introducing a new little piece of terminology here. The cyclo prefix means that you have a ring or something's cyclic. So cyclohexane, and hex means 6 carbons, and ane means an alkane, which is a saturated hydrocarbon. So all single bonds. And if I built this molecule of cyclohexane, and this is where we're looking at the top view, and we can sort of see why I might call it a crown. It's a hexagonal crown, and if we turn it sideways, you can see that there's sort of a base that it sits on with 3 of the hydrogens pointing straight down, and then all the adornment of the crown has to do with the hydrogens pointing to the outside or straight up. And so we're going to get into this structure quite a bit, try to view it from different angles and draw it, and focus on some of the terminology for different positions on the ring. So 6 carbons in a ring. The way this will be drawn traditionally is like this, and it's like we sort of tilted the molecule so the 6 carbons are tilted like this. So sort of overlaid the drawing and the molecule. So here's the head part as I see it, and then where you sit is the center part, these 4 carbons, and then your feet will be down here. So sort of like a chaise lounge. And when I turn this a little sideways, then the hydrogens are pointing a little bit sideways, but we're going to draw them either straight up and down or substantially off to the side. But this is where carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 in the ring, sort of drawn like a little chaise lounge. Head part up here, feet part down there. And I don't know if that makes any sense to you, but that's traditionally the way it'll be drawn. Now I've mentioned that some of these hydrogens point straight up or straight down, and those are called axial positions. So if we viewed a globe like this, actually that looks more like an egg, but if we visualize a globe, it rotates on its axis and it has an equator. So axial points straight up and down, and the equator is around the belly of it. So that's the way they visualize the cyclohexane molecule, is the plane of the ring is like cuts through the equator, and then some of the hydrogens are going to point either straight up or straight down. Every other carbon has a hydrogen that points straight up. And if I visualize sort of the plane of the ring again, 3 of the carbons are just a touch above the plane, and those have hydrogens that point straight up attached to them. So that's the way we draw it in the picture. 3 of the hydrogens on the other carbons, so 3 of them alternating carbons are above the ring. The other 3 are a little bit below the plane of the ring, and those have hydrogens that point straight down. And that's where if you build the molecule properly in this configuration, and you just put it down on the table, it stands on the 3 hydrogens that are pointed straight down. So if I rotate it like this, you can see the legs, the 3 legs, which are pointed straight down. Getting the orientation right here is a little tough. Pointed straight down. If I orient it like this, it sits on the bottom. You can see what's down, so those 3. And that's every other carbon. So this is pointed straight down, this carbon's a little lower. This carbon's a little higher. Its hydrogen is pointing straight up, not straight down. So each of the 6 carbons has an axial hydrogen, and they sort of alternate straight down, straight up, straight down, straight up, straight down, straight up. And so whenever I want to draw the chair form of cyclohexane, I go ahead and draw it like this, draw the chair, and then put in the 6 axial hydrogens. And then you look, there's also hydrogens like this guy that rather than pointing straight up and down is pointed mostly out to the side. But this one's pointed a little down. So if you look at the plane of the ring, the carbon that's a little higher than the plane of the ring has a hydrogen pointing straight up. It also has a hydrogen pointing mostly to the side and a little down. So that's what I'm going to draw here. This hydrogen is pointing mostly to the side and a little down. So the up and down ones were called axial hydrogens. The ones around the belly are going to be called equatorial, much like the equator, and that'll help you spell it right, because a lot of people try to spell equatorial like the word quit is in there, but it really is the word equator is in there with an A. And so equatorial and axial positions, this guy's an axial hydrogen, this one's an equatorial hydrogen. And one of the things with these positions is the equatorial hydrogen is pointed mostly out into empty space and doesn't bump anything else. So again, we're talking about hindrance or repulsions. That's called steric repulsions. So steric repulsions have to do with size related. So steric is having to do with size. Steric repulsions mean higher energy. And the things that are close to each other, even though they don't look like it in the drawing, are the axial hydrogens are fairly close to each other. So if you look again at the model here, this axial hydrogen is pretty close to this axial hydrogen. They're lined up almost like you can consider them to be eclipsed, that they're lining up with each other. Whereas if you look at the equatorial hydrogens, the ones that are pointed out to the side, they have a whole bunch of empty space around them. They're not close to pretty much anything, so the equatorial positions are roomier, and there's lots of space, no repulsions there. That'll be important when we get to substituted cyclohexanes. The thing that is also good to think about is once I've drawn in the axial hydrogens, which are really easy to draw in, I put in the equatorial hydrogens, and this business of whether something's pointed towards the top of the ring or the bottom is really important. So this hydrogen is pointed towards the bottom of the ring, or below the ring, towards the ground, and it's axial, pointed straight up or down. And then if this one's down, the equatorial one, the corresponding one on the same carbon, is going to be pointed a little up. So if the axial position is up, the axial hydrogen is up, the equatorial on the same carbon is down. So I always draw in the axial ones first, and then put in the equatorial ones, so I make sure I draw them the right way. If the axial is up, the equatorial goes down. If the axial goes down, the equatorial goes up. If the axial goes up, the equatorial goes down. And this would be a good representation then of the 6 carbons, which I did not draw in, sort of skeletal in that respect, but then I drew in explicitly the 12 hydrogens, 6 axial, pointed either straight up or straight down, and then 6 equatorial, which are pointed mostly out to the side, but a little up or down, depending on which carbon they're on. So it's going to be very important to understand top of the ring or bottom of the ring, axial or equatorial positions, and to be able to draw a decent chair form of cyclohexane, which is the lowest form. It minimizes repulsions. There's the molecule, and if I hold it right, like this, you can sort of see why they call it a chair. There's other configurations, like the boat form, where rotation about single bonds brings the molecule into a different shape. And with this model set, things are a little sticky, so it's harder to make these bonds rotate and everything so that I can show the different conformations. But this one is the boat form, and you can sort of see it's like a little boat with a bow and a stern. Again, getting these to sit in the right conformation with this sticky model set, the one we have in the lab, is a lot easier to manipulate. Trying to get it into a good boat conformation is a little difficult, but there it is, boat, where rather than having a head and a foot, it's sort of got two heads aimed at each other, and that causes a lot of steric repulsion between groups that ends up aimed at each other. So we're not going to deal with the boat conformation really at all in class. We're just going to look at the chair form, which is the most stable form of cyclohexane, and understanding which positions are axial and equatorial and being able to draw a good chair form are going to be important.